All right. So just to kind of give an overview of what we've done and where we're going before we start on anything new. So if you remember when we talked about this course in the very, very beginning of the year, I talked about how this course was going to be kind of a survey of functions. So this first chapter, what we've talked about are functions kind of in general and what the properties of functions are and some ways to describe them. The majority of the rest of the course we're going to be spent talking about different types of functions. Specifically, in this next chapter, we're going to talk about absolute value functions. And for each type of function, yeah, I'm going to live. All right. We're going to be primarily concerned with three skills. Those three skills are going to be simplifying, solving, and graphing. Now, some sections or some of these chapters are going to have more than just these three skills, but none of them would have less than these three. So these three skills are going to be a major part of every chapter. Every time we talk about a new type of function, our primary concern is going to be how do we simplify algebraic expressions involving this type of function, how do we solve equations using this type of function, and how do we graph this type of function. Everybody okay with that idea? So again, just trying to give us a little bit of framework. The tools that we developed in this first chapter, we're going to use over and over and over again in each of these different function groups. So in each of these function groups, we'll be concerned with domains and ranges. We'll be concerned with extrema, mins and maxes. We'll be concerned with graphing while thinking of it as a transformation. Over and over again, we're going to be using these same skills that we developed in this first chapter, which is why we spent a lot of time in this first chapter really working on these skills in a very general way. Notice that most of the time you weren't told what the function was, you're just called a generic f of x. Because we're going to be using that same skill over and over and over again for specific functions later in the course. Okay? So again, hopefully that feels useful to you to kind of get a picture of what we've done and how that applies to these topics going forward. The next chapter that we're going to look at is chapter 2. The book calls these modules, by the way. I'm just probably going to call them chapters. Is about absolute value functions. And our first lesson is going to be about graphing. But before we can really spend any time talking about graphing, we need to first define what we mean by an absolute value and talk enough about simplifying so that we're able to do these kind of graphing problems. Okay with that plan? Okay. So let's start with a definition. So this first definition that we're going to give is a geometric definition. Hello, Palmer. Thank you. So our geometric definition for an absolute value says that the absolute value of x is the distance between x and 0 on the number line. So, for example, if we want to talk about the absolute value of -5, if I think about this using the definition, so here's 0, 1, 2, 3, 4, -5. The absolute value of -5 is this distance here, the distance between -5 and 0 on the number line. If I count this up, I count 1, 2, 3, 4, 5 units. So I can say that the absolute value of -5 is just 5, because it's 5 units away from 0 on the number line. Everybody okay with that idea? Now, this definition is probably not the intuitive sense that we have for absolute value. Most of us know a little bit about absolute values already. And probably when we think about absolute value, we're just thinking about it as it gets rid of the negative sign, right? It makes any negatives positive, and any positives just stay positive. Now, the reason that is because distance as a measurement is inherently a non-negative quantity. Like if I called you on the phone and asked you how far are you away from me, and you said -2 miles, I'd look at you like you had a third head growing out of you or something, right? Like that answer makes no sense. You're just 2 miles away. The direction in which you are away from me doesn't matter. It's just the distance is 2 no matter what direction that you're in from me, right? So distance is inherently a positive quantity, which is why this geometric definition results in a positive value for all absolute values. I guess I should say non-negative. It could be 0, right? Everybody's okay with that idea? So there's also an algebraic definition. So my algebraic definition for an absolute value is just written as an equation. So I have the absolute value of x equals, and I have this big squiggly bracket. And what I'm writing here as a special name, it's called a piecewise function. And I'll explain to you guys in a minute why we call these things a piecewise function. So we call this a piecewise function because there's 2 equations here, and depending on what our input is, we'll do one or the other. Basically, that this function is broken up into 2 pieces. So if x is greater than or equal to 0, we do one thing, and if the input is less than 0, we do another thing. So it's broken into 2 pieces, so we call it a piecewise function. And this looks a little bit intimidating to look at, but it's not so bad. So again, if we wanted to take the absolute value of -5, the way we look at it is my input is less than 0. So what the piecewise function tells me to do is I take that input and I make it negative. So I'd have negative of -5, which is +5. If I had the absolute value of just 5, so here my input is non-negative, so the equation tells me that the absolute value is just that input, which is +5. So again, it's doing the same thing. It says if the number where you're taking the absolute values is positive, you don't have to do anything. You just get that same number back. If the number you're taking the absolute value of is negative, you should negate it, because the negative of a negative makes it positive, which gives you the positive number back. Juan, you were getting ready to ask something there. Right, so I'm giving you these multiple different definitions because depending on what you're asked to do in a problem, one or more of these definitions might be useful. Now, if I'm just asking you to take the absolute value of -5, the algebraic and geometric definitions aren't terribly useful. You know intuitively that just the absolute value of -5 is +5. But if this is part of like a story problem, one of these interpretations might be more useful into kind of unpacking how to do a story problem. So that's kind of why I'm giving you these other ways of thinking about what an absolute value is. Because depending on what you're being asked to do, one of these might be more useful than another. Does that make sense? Okay. And now, for the most part, your intuitive sense that the absolute value of just gets rid of the negative is fine, right? For the most part, that's practically going to be the most useful one. There may be instances where you're dealing with like a real-world situation where that becomes not as useful, and a geometric interpretation might be more useful. Or this algebraic definition might be useful if you're wanting to try to like do a proof or something like that. Now, we wouldn't do much proof in this course. But it's a very specific definition that's useful depending on the context of what you're trying to do. Okay. So hopefully at this point we feel okay about what an absolute value is. So I want to talk a bit about how we simplify absolute value expressions. And I'm not going to do a ton of this today. I just want to do enough so that we can do the graphing things. So I'm just going to write down some rules here, and we're going to decide whether what I'm writing down is kind of true or is it false. Okay with that idea? So what I'm writing down right now, we're not sure if this is a rule or not. We're going to take a minute and decide together whether this is true or false. So my first statement is the absolute value of x plus y equals the absolute value of x plus the absolute value of y. Basically what we're saying here is that I can break an absolute value at an addition symbol, right? Can we kind of see that that's what this is saying? What do you guys think? Is this true or false? Okay. So if it's true, we should be able to pick specific values of x and y and have them satisfy this equation. So let's pick a value for x. Seven. Sounds good. And let's pick a value for y, but since absolute values really concern negatives, let's make sure we pick a negative value for one of these two. So since we picked a positive x, let's pick a negative y. -9. Okay. So if I plug these in then, I get 7 plus -9. Take the absolute value. Absolute value of 7 plus absolute value of 9. 7 plus -9 is -2. The absolute value of 7 is 7. The absolute value of -9 is 9. 2 does not equal 16, right? So what can we say about this statement? It's false. Those two things are not equal. This is one of the most common mistakes I see students make with regard to simplifying absolute value functions, is that they break the absolute value at addition or subtraction, right? If it doesn't work for addition, it won't work for subtraction. Everybody okay with that idea? So very important that you do not do this. If you do this on a test or a quiz or something, this is something that would warrant a big deduction. This is kind of a fundamental rule that you never want to do this when simplifying. And you might think, Mr. Kulik, how is this a common mistake if you're sitting here telling me I never can do this? Like, why would I be confused that I can do this? Well, let's look at the next rule. We have the absolute value of x times y equals the absolute value of x times the absolute value of y. What are we doing here? We're basically asking, is it okay to break the absolute value symbol at a multiplication? What do you guys think about this? This one does work. Yeah, let's pick the same two values for x and y and just kind of convince ourselves that this does work. So this one does. And this is why students get confused at when it's okay to break that absolute value symbol and when it's not. So you can break your absolute value at multiplication and divisions. You cannot break your absolute value at addition and subtraction. Everybody okay with that? So please make sure that you're being very careful about that. What about this? I just made everything positive inside the absolute value. Is that okay? Definitely not, right? What are we basically doing here? If this was to be true, we're basically violating rule 1, right? I can't take the absolute value of these pieces individually because there's an addition or subtraction symbol involved. So it's a whole shot or no shot. Okay with that? One special note. Let's say we have the absolute value of 2x plus 4. Can I simplify this at all? So I can use rule 2 on this. We have to be a little bit careful, though, on how we get to that place where we can apply rule 2. So Nancy noticed that both of these two terms are divisible by 2. So what that means is I can take a greatest common factor of 2, and I can rewrite it as 2 times the quantity, x plus 2. Now that I've written this as a multiplication problem, I can apply rule 2 to rewrite this as the absolute value of 2 times the absolute value of x plus 2. And we know the absolute value of 2 is just 2. Is everybody okay with that idea? This is something that you'll need to remember to do when we're doing our graphing homework tonight, because it'll be important in making sure you can correctly identify the value of A in our problems. Everybody see what we did there? Kind of sneaky, wasn't it? You're like, I can't use property 2 on this. There's no multiplication going on between two things. A little bit of factoring proves kind of otherwise, right? Okay. So let's move on and start talking about graphing. So the way that we're going to graph these absolute value functions is using transformations. So in this case, our parent function for absolute value functions is just y equals the absolute value of x. So let's take a look at that absolute value of x. So the absolute value of x contains 3 key points. Negative 1, 1, 0, 0, and 1, 1. And the graph of all absolute value functions is going to look like some version of the parent function. So it's going to look like some transformation of this V graph. This point, the tip of our V, has a special name. We call this point the vertex. So recall, we had for a parent function y equals f of x, our transformation function was equals a times f of x minus h plus k. In this chapter, we're dealing with the specific function, parent function, y equals the absolute value of x. So our transformation function is going to look like a times absolute value x minus h plus k. So again, what I'm trying to do here is relate this material that we're currently working on back to the general concepts that we developed in Chapter 1. So my plan is going to be identify the A, H, and K, and then use my transformation map to transform those 3 key points. That's going to be my plan to do this graphing. So I'm going to just identify the A, H, and K, and I'm going to write a transformation map and use that transformation map to transform those same 3 key points and then graph my new transformed points. So let's see an example of us doing that. Sound good? Let's say we want to graph y equals the absolute value of x plus 3 plus 1. First goal, or first step, got to identify those values for A, H, and K. What's my value for A? It's not 0 because A is being multiplied. So if there is no A and it's being multiplied, what number is really there? 1. What's my value for H? Negative 3. Remember, the H is always the opposite sign of what it appears. And my value for K is 1. Everybody okay with that? What I'm going to do next is write my transformation map. So I'm going to have my xy's are going to be transformed using x minus 3. And then 1y, I don't need to really write the 1, right? Plus 1. So again, plugged in my values for A, H, and K. And now I'm going to use my 3 key points. Every time I graph an absolute value function, I'm going to use those same 3 key points. So when I plug those values in for my x and y, I get, for the first point, negative 4, 2. the second point, I get negative 3, 1. And for the third point, I get negative 2, 2. So now all I'm going to do is plot. So I have negative 4, 2, negative 3, 1, and negative 2, 2. So there's my graph. If I were to describe this transformation in words, my A value is positive, so I have no reflection. My A value is 1, so I have no stretch or shrink. My H is negative, so I'm going to go left, and because it's negative 3, I'll go left 3 units. And then my K is positive, so I'll go up, and my K is 1, so it'll be up 1 unit. Which is exactly what it looked like, right? If my parent function was here, what did we do? We went left 3 and up 1. Can everybody see that? And we can do this same procedure for all absolute value functions. It'll always give us a nice graph without having to do anything more than like some addition and subtraction. Okay. Both. Yeah, there'll be times where I ask you to describe the transformations. There'll be times where I ask you to just graph the thing. There's times I might ask you to do both. Again, I think that the two reinforce each other. They're a good check. You know what I mean? So if I write, like this should be the transformation, I look at my picture and it's like, that ain't at all what I said was supposed to happen. It gives you some, to go back and take a second look because you've made a mistake someplace, right? So I think the two are really helpful in that if I know what this graph should look like before I start graphing it, that helps me know that when I finish if I've done this correctly or not. Let's do one more. So let's say we have negative 2 times the absolute value of 3 times x plus 2 minus 1. What's different about this than the previous one? We have that 3 stuck in there, right? What should I do before I get started? I'm not going to distribute that 3. I'm going to use property 2 to move that 3 outside the absolute value. Everybody okay there? And we know the absolute value of 3 is 3. And negative 2 times 3 is negative 6. And the reason I don't want to distribute there, Justin, even though you can, it's not wrong to do that, but if my goal is to be able to find A, H, and K out of there, the leading coefficient on X has to be 1. If I distribute the 3, that is no longer the case, right? So it just doesn't get us closer to where we're trying to get to. Not that it was wrong to do that. It's okay. There's nothing mathematically wrong about doing that. It just wasn't helpful to do that. So if I look at this situation now, I'm in a form where I can find my A, H, and K. The A is negative 6. The H is negative 2, very good. And the K is negative 1. And just like before, I'm going to write my transformation map. So I'm going to have x plus h, a times y plus k. And then I'm going to perform that transformation on these same three key points. Every time I graph an absolute value function, I'm using these same three key points. Oops. When I do that, I get negative 3 minus, or negative 3, negative 7. I get negative 2, negative 1. And I get negative 1, negative 7. So let's negative 3, negative 7. Negative 2, negative 1. Negative 1, negative 7. Just miss that a little bit. And if I was to describe this transformation in words, I notice that my a is negative. So I reflect across the x-axis. The magnitude of a is greater than 1, so I have a vertical stretch. My h is negative, so I'm going to go left, and because it's negative 2, it's left 2 units. My k is negative 1, so that's going to be down, and then because it's negative 1, it'll be 1 unit down. Which is, if I compare this to the parent function, is exactly what it looked like, right? We flipped it upside down. We stretched it vertically, like you're in a fun house or something. You've seen the mirrors that make you look tall and skinny. That's what we mean by vertical stretch. And then we moved it left and then down. Everybody feel okay about generating these graphs? Okay. Yes, Justin. Of course. You can go too, Katie. Do you want? Yeah, of course. So what we're going to do next is we're going to collect some observations. So in chapter 1, we were really concerned with like domains and ranges and increasing, decreasing, and extrema and things like this. We're going to formalize that now for all absolute value functions. Our goal is to be able to figure out these kind of descriptions without actually having to look at the graph for the absolute value function. We're going to use the observations that we can make from these two graphs that I've drawn and what we know about transformations so that we can come up with a set of rules to describe the domain and range for all absolute value functions, the increasing and decreasing for all absolute value functions, the location of the vertex for all absolute value functions, etc., etc. Everybody okay with that? All right. Joanne, you good? Okay. So, first things first, I want to talk about the location of the vertex. Remember, the vertex is the point of our graph. So in this one, our vertex is at -2, -1. For our first example, our vertex was at -3, -1. If I look at those numbers, do they hold any significance? Well, -3, 1 was my h and my k. And down here, -2, -1 was also my h and my k. And it turns out that the vertex is always located at that point, h, k. So without even graphing anything, I can look at the equation, determine the value of h and k, and immediately know the location of the vertex. It's a pretty good deal. Next thing, let's talk about the domain. Notice that my graph is always going to have a left arrow, so there's no leftmost point, and always have a right arrow, so there's no rightmost point. So for all absolute value functions, the domain will be negative infinity to positive infinity. That's really nice when we can say something about every single time we're dealing with the domain of this function, it is this, right? Takes away having to figure that out. The range is not going to be the same every single time, but it's going to be one of two things. So if I look at my first graph, I have no lowest point, but I do have a highest point. If I look at the other graph, I have a lowest point, but no highest point. So depending on whether my graph looks like a V or a wedge, I can determine what the range is going to be. So if the graph is a V, my range is going to be the lowest point, which occurs at the vertex. And since we're talking about ranges, it's the y-coordinate of the vertex we're concerned with, all the way up to positive infinity. And if the graph is a wedge shape, we're going to start at negative infinity and go all the way up to that highest point, which is the vertex. And since we're talking about ranges, we're going to talk about the y-coordinate of the vertex. Now, is there a way for me to look at my equation and be able to determine whether my graph is V-shaped or wedge-shaped? There is. I just need to worry about the sign of that A. So if A is positive, there's no reflection. It'll look like the parent function. It'll be V-shaped. If the A is negative, there is a reflection, and it'll look like a wedge. Everybody okay with that idea? Next, let's talk about increasing and decreasing. So if I have regardless of the shape of my graph, whether it's a V or a wedge, I have one section that's increasing or decreasing, and the other section would be the opposite, right? Everybody agree with that? So if we are V-shaped, we start out decreasing, and then we finish up increasing, right? Everybody agree with that? So my increasing starts at the vertex, so the x-coordinate of the vertex is h, and it continues increasing for the rest of the time. If I have a wedge shape, we start out increasing all the way to the vertex whose x-coordinate is h. If we're talking about decreasing, so if I have a V shape, I start out decreasing and stop at the x-coordinate of the vertex. And if I have a wedge, I'm starting at the vertex and decreasing all the way out to positive infinity. Yes, sir. Of course. For the extrema, notice at any time we're only going to have one extrema for an absolute value function. That one extrema is always going to be the vertex. It's always going to be either a global minimum or a global maximum. If we have a V shape, it's going to be the global minimum because the lowest point is at the vertex. If it's wedge-shaped, we're going to have a global maximum at the vertex because the highest point is at the vertex. Everybody okay with that idea? So the end behavior, notice on the two graphs we drew, either both arrows pointed up or both arrows pointed down. Those were the only two options. We never had a situation where one was up and the other was down. Everybody agree? Okay. So if I have a V shape, both arrows point up. So when we say X, or we say the left arrow points up, and we say the right arrow points up. And if we're wedge-shaped, we have the left arrow points down, and also that the right arrow points down. Yes, sir? Global. G is for global, as opposed to local. Yes?
So if you can tell what it's going to look like based off of all the observations, why do you use the equation?
So if we want the actual specific graph, that's how we graph it. But this is what we're doing here, is saying, what if I just care about these descriptions and I don't actually care what the picture is? Can I figure these things out without having to look at the picture? Which is what we're trying to do here. And oftentimes in mathematics, that's what we're trying to do, is we're saying, okay, yeah, sure, I could figure this information out from looking at the picture. Can I do it without having to get the picture, though? What if my function isn't represented as a graph, but it's represented as an equation? Can I still figure the same information out without actually having to get the graph? Yes? Oh. So what? Oh, sure. Yes, of course. All right. Madison, you're good? Okay. We're going to do one example here, and then we're going to be done. So let's say we want to analyze the graph. Y equals 3 times the absolute value of x plus 1 minus 3. I'm going to start by identifying the values for A, H, and K, because I need these to do all my analysis. What is my value for A? My value for H? -1. My value for K? -3. Everybody good? So from this, I can tell the vertex. What's the equation for the vertex? H comma K, so -1, -3. I can tell the domain. The domain is always negative infinity to positive infinity. And I can tell the range. Since the A value is positive, I have a V or a wedge. Which one? A V. So since it's a V, I'm going to have a K to positive infinity. So again, increasing and decreasing. Since this graph looks like a V, we start out decreasing, and we decrease all the way to the x-coordinate of the vertex, which is H. At H, we start increasing, and we increasing all the way out to positive infinity. Since my graph is V-shaped, do I have a global minimum or a global maximum? Okay, so I have a global minimum, and that global minimum is at HK, the vertex. The end behavior. So, because my graph is shaped like a V or a wedge, which one? V, because the A value is positive. Both ends of the graph point up, or do they point down? For a V. The ends of my graph point up. So y should go to positive infinity or negative infinity? Positive. Okay with that? So look at all this great information we got. We didn't have to draw the picture. All we did was use our observations.